Hello, everybody. Welcome back. Today, we are going to be talking about higher order derivatives and the minimum and maximum values. Now, I want to be clear, this doesn't just have to do with the global minimum or global maximum, the way we would have to think of it in terms of domain, range, that sort of thing. This has to do with both the extreme values, but also the local minimums and maximums. So, the minimum or maximum in a specific area, or a turning point is another way to look at it. So I'm going to talk about some different extreme values. In this case, our absolute maximum is right here. This is our absolute maximum because there's absolutely no other value that is higher than this maximum. So there's our absolute maximum. And here is our absolute minimum because there is no other point that's lower, right? Now, let's talk about the second example. Here we still have this point as our absolute maximum, right? That is still the highest point. But this point here is not our absolute minimum anymore. We have an even smaller minimum, which is this point right here. So this is our absolute min. However, this point over here, this is still the minimum in the area. It's still a turning point where we switch from decreasing to increasing in value, right? And so this is still a minimum. It's just called a local min or a local minimum because it's not the absolute lowest point. It's just the lowest point in that specific part of the graph. Now, what about this third graph? Well, this point is not any longer our absolute max. This is a local max because we have an even higher maximum up here. So this is our absolute max. And likewise, this is not our absolute minimum. This is just a local minimum because the actual minimum is even lower, even smaller number with respect to y. And this is our absolute minimum. So when it comes to curve sketching, which we're not going to tackle yet, but we will tackle it in calculus and vectors, we will be tackling it in this course, it's important to know where these values are, right? In advanced functions class, you were probably told, don't worry about where the turning points are. And the reason you were told that isn't because it's not important to find them, it's because in order to find them, we have to use calculus methods in order to do that. And that takes a lot, right? That's a whole other can of worms that we weren't going to open in advanced functions, but that we are going to open now. In advanced functions, we focused on finding the end behavior. We focused on where is the function positive, where is it negative, where are the zeros, and that gave us a pretty good idea and a fairly accurate graph. But the parts of the graph that we couldn't actually make accurate were the turning points and the concavity. And this is going to help us in order to do that, which is going to be talked about more in the next unit. So let's talk about finding maximum or minimum extreme values. And this comes up in this unit. It'll also come up in the next unit as well. So this is quite important. Okay, so here it says, if a function f of x has a derivative at every point in the interval, then we can calculate f of x at all the points on the interval where f prime of x is equal to 0 and at the endpoints, right? So if it's a function that has endpoints, we need to figure out what are the values of the endpoints, and also where are the values where f prime at x is equal to 0, right? Because again, if the derivative is 0, that means the slope of the tangent is 0, and at every turning point, every minimum or maximum, whether it's the global or local, right? Or I should say for every local max or min, it's going to have this. But the other place where we might have minimums or maximums is the endpoints. Now, if the graph was actually continuous, forever for the entire negative infinity to infinity, then those endpoints would just be the infinities, right? Would just be infinite. But and so there wouldn't actually be endpoints. But in this scenario, they're giving us certain endpoints for this function. So that's why we must check the endpoints. And we also must check the f prime of x values in order to know. Because sometimes those turning points will happen to be the global minimum or maximum. And sometimes they'll just turn out to be a local minimum or maximum. When it says determine the extreme values, what they mean by that is all the local minimums and local maximums and global minimums and global maximums. And they also want us to not just state the values, but also state what's what, right? Is this a global minimum? Is this a local one? And so on. And another important quick note is that only the turning points are guaranteed to be an extreme value, right? Just because something is an endpoint doesn't necessarily mean it's the extreme value. So, for example, here, these are the endpoints, but notice I didn't write anything. These are not extreme values. There's nothing special about them. Or this endpoint, nothing special about it. I only actually care about the endpoints when they actually go more extreme, when they are more extreme than the local minimums and maximums. And so the endpoints are just because something's the endpoint does not mean it's an extreme value. However, a turning point is always an extreme value. It just might not necessarily be the global extreme value. Okay, so with that all said, let's go ahead and answer this question. It asks, determine the extreme values of this function on this interval. So first thing I'm going to do is I'm going to find f prime of x because we need to set it to 0 in order to figure out which points we're looking at, right? So let's do that. The derivative is negative 6x squared plus 18x. And we're going to set this to 0 because we want to find the extreme values. So 0 is equal to negative 6x squared plus 18x, which means that this is our answer. Now, one common mistake I often see people make is canceling out the x, and when we do that, we actually lose a value. We lose the x equals 0, so you will still get the x is equal to 3, but we will not get the x equals 0 if you do decide to cancel out that x. So make sure you don't do that because we do want both those values, and in fact, we need both those values. Okay, so those are the two x values. So now what I'm going to do is I'm going to figure out what y values are associated. So f of 0 is just equal to 4, right? Because these would just be gotten rid of. And f of 3, if we did the math, we would figure out that f of 3 is equal to 31. I will do it out. I'll show why it's 31. Plus 9 times 3 squared plus 4 is equal to negative 2 times 27 plus 9 times 9 plus 4. So that's going to equal to minus 54 plus 81 plus 4, which is equal to 31. So there we have it. So two extreme values so far that we have are, we know that there is at 0, 4, there is an extreme value, and at 3, 31, there's an extreme value. But what we don't know is, are they minimums or maximums, or what types, right? We need to continue on with the endpoints to know what types. So now let's find the endpoints. So let's find out what f of negative 1 is equal to, and also what f of 5 is equal to. So actually, you know what? I'm sure we know how to do that. F of negative 1 is 15. F of 5 is negative 21, right? Same way that we figured out f of 3, just plugging that in, I'm sure is something we all know how to do by this point, I would hope. So there we go. So now let's talk about what's what. Well, we have a point at negative 1, 15, right? So 15 is a value and negative 21 is a value. And so in this situation, we can clearly see that our maximum would be 331, right? This maximum we got here is going to be our global max. Why is that? Because none of the endpoints reached it, right? The maximum of our endpoints was just 15, so this must be our global maximum. Now this one is just a local min. And how do we know that? Well, because our global minimum, we actually got something less than 4, which was negative 21, which is certainly less than 4. So therefore, this is our global minimum. So basically, How this works is we look at the original extreme values that we get and state that they are the global maximum and minimum. If they are more, or if they are higher or lower, depending which extreme value they are, than the endpoints. Now, if they are not, like with the minimum, we just say, okay, well, then it's just a local minimum because we have an actual, even smaller minimum at our endpoint, which in this case we did. And notice how negative 115 was never mentioned again after this, because this endpoint did not end up being a more extreme value than the other one we found, so we can just ignore it. All right, well, that's our first one done. Let's do 2 more examples for this lesson. Okay, the amount of current in amperes in an electrical system is given by the function C of t is equal to negative t cubed plus t squared plus 21t, where t is the time in seconds, and 0 to 5. X goes from 0 to 5, including 0 and 5. Determine the times at which the current is at its maximum and minimum, and the amount of time and the amount of current in the system at those times. Okay, so first thing we're going to do is we are going to figure out what are our minimums and maximums. So to do that, we need to set the derivative to 0, right? Because setting the derivative to 0 gives us our extreme values. So let's do that. 0 would be equal to negative 3t squared plus 2t plus 21. So that means 0 is equal to, if we were to factor this using the quadratic factoring methods that we know, we would get this as our answer. So that means that t equals 3, or t equals negative 7 over 3. But keep in mind, negative 7 over 3 is not part of the interval. This is not applicable to this situation because it is outside of the interval from 0 to 5, up to and including those 2 values. Okay, so therefore, we're good. Now all we need to do is figure out the endpoints. So let's figure out the endpoints, and also let's figure out C of 3. So C of 3 is going to be equal to negative 3 cubed plus 3 squared plus 21 times 3, which is equal to negative 27 plus 9 plus 63, which equals to 45. Now what about C of 0? Well, that's easy. That's just going to be 0. And then C of 5 is equal to negative 5 cubed plus 5 squared plus 21 times 5, which is equal to negative 125 plus 25 plus 105, which is equal to overall, I believe it's just 5. Yeah, it's just 5. Okay, so what can we conclude from this? We can conclude that the maximum must be this value here, the 345, because 45 is the biggest number out of all 3 of these, right? So out of all 3 of these, the biggest number was 45, right? So therefore, the maximum max current was 45A, right? Now what about the minimum current? Well, the true minimum current, according to the function, would have occurred here, right? This would have been our extreme value. However, we couldn't get that far because it's not in the interval. So therefore, our minimum would have been 0. And also having a negative amperes potentially may not have made sense for this situation, right? And so remembering the real life situation it is key here, because otherwise, what's wrong with having negative 7 over 3 as one of our values? It doesn't seem wrong at all until we consider the situation that we're looking at. So the minimum current would just be 0 amperes. And it says, and the amount of time as well. So the time that goes with this one is t equals 3, and the time that goes with this one is when t equals to 0. So we get to our minimum when t is 0, it's 0, and then it goes up. And the highest that it goes is to 45 amperes, and that occurs after 3 seconds. Very good. All right, let's do one more last example here. It says the amount of light intensity on a point is given by this function, where t is the time in seconds. Determine the time of minimal intensity. Okay, so let's do this one next. So first things first, we need to take the derivative, okay? We need to find the derivative. And to do that, we're going to use the quotient rule. So if you're unfamiliar for how to find the derivative of a quotient, make sure you go review the quotient rule video. But basically, the quotient rule is derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. So let's do that. Derivative of the top is 2t plus 2 times the bottom, t plus 2, minus the top, which is just t squared plus 2t plus 16, times the bottom, which is 1, which I'm not even going to bother to write times 1 because that doesn't really do anything for us. And that's over the bottom squared, so t plus 2 squared. Now I'm going to expand and simplify this, and also we're going to set it to 0. So once we set it to 0, the t plus 2 squared that just comes on the other side, just kind of disappears. So here we have 2t squared plus 4t plus 2t plus 4 minus t squared minus 2t minus 16 is equal to 0. So 0 would be t squared. And then let's see, and then these two cancel out. So we just have plus 4t. And then we have these two to add together. So we're going to have minus 12, I believe. Yeah, minus 12. Okay, and now we need to factor this or use the quadratic formula in order to solve. I'm going to use the factoring method because it's much easier and faster, but the quadratic formula works as well if you really don't like factoring for whatever reason. There we go. So therefore, t equals to negative 6 and t equals to 2. Now, t equals negative 6 is not applicable because it is not in the interval, and also negative time doesn't really make sense. Usually when we're talking about time, we only think about positive time as opposed to times in the past because we're starting, this exercise during the beginning of the experiment, not whatever we did yesterday before we even thought of this experiment to throw the ball or find the light intensity or whatever the case may be. Okay. So t equals negative 6 is not applicable, so we only need to check I of 2 and then also the endpoint. So I of 2, I of 0, and I of 14. So the endpoints and also the extreme value that we found. So I of 2, well, that's going to be 2 squared plus 2 times 2 plus 16 over 4, which is 4 plus 16, so 24 over 4, which is 6. I of 0 is just going to be 16 over 2, right, which is 8, because we can just ignore everything with t and only look at the constants for that one. And then I of 14 would be 14 squared plus 2 times 14 plus 16 over 14 plus 2. So that's equal to 196 plus 28 plus 16 divided by 16, which is equal to 15. Okay, so what's our highest value here? Or actually, no, they just asked for minimal intensity. My apologies. So what's the lowest number here that we got? Well, 6, right? 6 is lower than 8 and lower than 15. So therefore, the minimal light intensity is 6. And that occurs, which occurs at t equals 2 seconds. Because actually, I'm just realizing they actually asked determine the time of the minimal intensity. Now, so does that mean that we could just have found the 2 and then written that down, that that's the answer? Well, technically in this case, had we done that, we would have absolutely been right. But in general, it's not a good idea to make that assumption, because what if I of 0 had ended up being even less? Then that would have been the minimal intensity, right? So we didn't know which time was truly going to lead us to that smallest output, to that smallest minimal intensity, until we plug the numbers in. So even though, yes, they didn't even ask for the 6, they just asked for this number, we had to find the 6 and the 8 and the 15 in order to know for sure that 2 was associated with that minimum intensity. And so, as far as I'm concerned, this work we did here was not a waste. It was important to do to make sure that we got it right, even though, yes, technically we would have gotten it right anyway had we made an assumption that could sometimes give an incorrect answer, but in this case would have still given the correct answer. All right, well, that is it for this lesson. In the next lesson, we'll be talking about optimization problems. So it's just some word problems regarding the optimization. And until next time.